What's up, amigos? Today we're looking at the aerodynamics of a cylinder at a Reynolds number of 100 compared to 1000. So a few weeks ago, I did a simulation of a cylinder for the Reynolds number of 100 to see the Karman Street, and that was pretty cool. And I wanted to see what the effects were when you put the Reynolds number higher. And there's a lot of literature on this, but there's not a lot of videos on this. So we thought we'd do one on that. So the top video is the cylinder at a Reynolds number of 1000. The bottom one is of a Reynolds number of 100. And in the previous video with the Reynolds number 100, the straw number was about 0.162 from memory, which was exactly where it should be. In this video, the Reynolds number of 1000 means that the straw number is about 0.219, and that's again where it should be. So one thing that we should note is that when you look up the straw number of a cylinder with the Reynolds number, they do have a bit of a spread in the straw number there. And there are two reasons for that. The first one is that a lot of results do not take into account the term's tensity level. And what's more, the second reason is that a lot of results don't take into account the surface roughness of the object. Both of these aspects do change the vortex shedding behind a cylinder and behind a lot of bluff body objects. So in this particular case, we have the vorticity plotted for both of these Reynolds numbers, but if you look at the legends, if you can see them, I'll describe them to you. First of all, for a Reynolds number of 100, the legend goes from -30 to +31 seconds for the vorticity. For the Reynolds number of 1000, the legends go from -600 to +600, so it's 20 times the number, even though it's only a 10 times increase in the Reynolds number. So that means that the vortices coming from the top cylinder are significantly they have higher vorticity, and because they're about the same sort of size as the vortices from the Reynolds number of 100, we can pretty much conclude that the vortices on top are going to be stronger because they're about the same size but have a much greater vorticity. Another thing that we can see is, actually I should mention I've slowed down the von Karman Street of the top cylinder so we can see it in real time. If I were to put it in real time, it would be very quick. We wouldn't really be able to see much going on. It's just all these vortices being shed very quickly. So I've slowed it down. And another thing we can see, which is slightly different, is how the vorticity is being created at the front of the cylinder. So for the Reynolds number of 1000, you can see that there's like a very thin strip of high vorticity, whereas for the Reynolds number of 100, the vorticity strip is significantly thicker. Now, that is also a function of the plot that we can see, the scale, but still it is much thinner. Another major factor is where the flow is separating. So on the one on the bottom, and we'll see with the velocity plots and the pressure plots later, that the points at which they separate are slightly different. And this is because for the top case where the Reynolds number is 1000, the velocity is much greater, which means that there's a lot more energy in the flow near the boundary layer, in the boundary layer as well, which means that it can overcome adverse pressure gradients much better. And with a cylinder, as with any curved surface, as you go along the surface, the pressure starts to become much greater, which forces the fluid back and tries to get it to separate. So the higher the velocity in the boundary layer, the more you can resist that, which means that the flow can travel further downstream. And that's partly why we get a very different straw number as we go to different Reynolds numbers as well. Let's look at the velocity now. So now we have the velocity plots. Again, on top is the Reynolds number of 1000. On the bottom is the Reynolds number of 100. So the top one, the velocity is 10 times greater than the bottom one. And we can see that in the color bar. So the color bar ranges for the bottom one from 0 to 0.15 meters per second, because that simulation was conducted at 0.134 meters per second, I think, from memory, something like that. The top one, the color bar goes from 0 meters per second to 1.5 meters per second, because that simulation was conducted at 1.34, so 10 times the amount, the velocity. And a few things that are interesting. First of all, we see that the number of low velocity cores going along are pretty much the same as the bottom figure. So if you look at the part that is partitioned here, there are about 6 to 7 low velocity cores between the cylinder and the end of the screen. That's regardless of the Reynolds numbers. That means that the vortices that are being shed aren't actually any more compact. They just move faster. That's really all that happens with this Reynolds number. Another interesting thing that you can see is that the wake behind the cylinder is, for the Reynolds number of 1000, is significantly smaller than for the Reynolds number of 100. and that's just because the flow has more energy, so it can wrap around the cylinder better and make this wake smaller. Let's move on to the pressure now. So now we have the pressure plots, and again, the top one is for Reynolds number 1000, the bottom one is for Reynolds number of 100, and the scales are different. So the bottom scale ranges from -5 millipascals effectively to 5 millipascals, and the top one ranges from -0.8 pascals to 0.8 pascals. And really, the only major difference that you can see, because the coloring makes it look a little bit different than it really is, but one thing to focus on is the alignment of the vortices. So these vortices you can sort of tell from the low pressure core, so the blue little circles going along. And as you can see in the top video, these cores are significantly more aligned than the cores underneath for the Reynolds number 100. And one reason for that is because not only where they shed from, but also another reason is that the vortices upstream and downstream all affect each other, so they induce flow. And the reason why that happens is because of viscosity, obviously. These things are rotating around, so they're ripping fluid away around itself, and anything in its around it will be caught up in that as well and pulled a little bit. And because the vortices on the Reynolds number of 1000 are much stronger than the vortices on the 100 Reynolds number, they affect each other much more, and then you get this alignment happening. So that's in this video. Make sure to like, subscribe, and if you want to get better at CFD yourself, check out our courses in the link in the description. And if you want to get better at theory like this as well, check out the courses as well. And I'll see you in the next simulation. Peace out, amigos.